Hello, my name is Jenna Tran, and this presentation describes Lab 3 black holes in orbits for Physics 2211. In this lab, computational modeling and gravitational physics were used to analyze orbital motion and simulate gravitational systems. The presentation will first discuss the physics principles used in this lab, then explain the analysis used to determine the mass of a black hole, and finally describe the computational model used to simulate a spaceship orbit influenced by both a planet and its moon. The purpose of this lab was to apply gravitational physics and Newton's laws to analyze orbital motion in simulated systems. In part one, the motion of a star orbiting a black hole was analyzed in order to estimate the mass of a black hole. Part two, the goal was to determine an initial velocity that would allow a spaceship to move in an orbit influenced by both a planet and its moon without crashing. Two important physics principles are used. The first is Newton's second law, which states that the net force on an object equals the rate of change of its momentum. The second is Newton's law of universal gravitation, which describes the gravitational force between two objects based on their masses and the distance between them. These principles allow us to understand how gravitational force produces orbital motion. In part one, a star with a mass of 2 times 10 to the 30th kilograms orbits a black hole located at the origin. The simulation provides the star's position coordinates at different times. The time between each observation point is 1 Earth day. Using this motion data, the goal is to estimate the mass of a black hole responsible for the gravitational force acting on the star. Because the star's trajectory is curved, it indicates that a force is continuously changing the star's momentum. To determine the mass of a black hole, the code first calculates the star's velocities and changes in position over time. Then the initial and final momentum vectors are computed using the star's mass and velocity. The change in momentum over time gives the net force acting on the star using Newton's second law. Next, the direction of the force is compared with the radial direction toward the black hole. Since gravity is the only force acting on the star, the radial component of the net force must equal the gravitational force from the black hole. Using the gravitational force equation, the mass of the black hole can then be calculated. This calculation is repeated for many data points, and the average value is taken as the final estimate. From the simulation data, the average mass of the black hole is calculated to be approximately that number shown here. This result helps illustrate what the net force and the range of momentum means physically. According to Newton's second law, the net force of the star equals the rate of change of its momentum. This means that whenever the star's momentum changes, there must be a force acting on it. The net force can be broken into two components relative to the star's motion. The parallel component of the force changes the star's speed, while the perpendicular component changes the direction of motion. In an orbit, the perpendicular component is responsible for continuously bending the star's path, causing it to move in a curved trajectory around the black hole. In part two, a new system is simulated that includes a planet, a moon orbiting the planet, and a spaceship located near the moon. The planet is fixated at the origin, and the moon moves in a circular orbit around it. The spaceship begins just above the surface of the moon. The goal of this part of the lab is to determine an initial velocity that allows the spaceship to move in a stable orbit influenced by both the moon and the planet without colliding with either object. To simulate the motion of the system, the code calculates gravitational forces at every time step. The spaceship experiences gravity from both the planet and the moon. The gravitational forces from each body are calculated separately and then added together to determine the net force on the spaceship. Using Newton's second law, the acceleration of the spaceship is calculated from the net force. The velocity is then updated based on the acceleration, and the position is updated using the new velocity. By repeating this process many times, the simulation generates the trajectory of the spaceship over time. After testing different velocity values, a stable orbit was achieved when the x component of the spaceship's velocity was set to approximately 1.10 times the moon's orbital speed, and the y component was set to about 1.25 times the moon's orbital speed. With this velocity, the spaceship moves in a complex orbit influenced by both the moon and the planet. If the velocity is too small, the spaceship crashes into the moon. If the velocity is too large, the spaceship escapes the system. This demonstrates how sensitive orbital motion can be to initial conditions. So what if we model the entire system? If we wanted to model the motion of the entire system more realistically, the computational model would need to include gravitational interactions between every pair of objects. This includes interactions between the black hole, star, planet, moon, and spaceship. Each object exerts a gravitational force on every other object. However, not all forces contribute equally. The strongest interactions would likely concur between the most massive bodies, such as the black hole and the star, or the planet and the moon. The spaceship's gravitational influence on larger bodies would be extremely small due to its much smaller mass. Therefore, while all interactions exist, some dominate the motion of the system. Finally, we go to errors, improvements, and conclusion. So there are several possible sources of error in the simulation. First, the model uses discrete time steps to approximate continuous motion, which introduces numerical approximation errors. Second, the results are sensitive to the chosen time step size since larger time steps reduce accuracy. Third, the orbit of the spaceship is highly sensitive to its initial velocity, meaning small changes can produce very different trajectories. Possible improvements to the model include using smaller time steps for greater accuracy, extending the simulation time to analyze long-term stability, and including additional gravitational interactions between more objects. Overall, this lab demonstrated how Newton's laws in gravitational physics can be used with computational modeling to analyze orbital systems and estimate unknown quantities such as the mass of a black hole. Thank you.